first thing that we're going to sort of think about here is it helps to just think about rates of change. Like this could have almost been a grade 9 question that we're about to do, but it's interesting to look back. And in fact, there's a whole section of this text that we skipped that is basically a bunch of grade 9 questions revisited. But it's interesting with a better perspective and a better understanding to look back at these kinds of questions a little bit sometimes. That's kind of what this is like. I like these questions. So you were looking at, for this first one, a glass or a vase or something like that. Okay, and it's being filled with a constant rate of water. That's important. So somebody's pouring a pitcher of water or a hose, or the tap has been turned on and it's flowing at a constant rate. You'll always see that. If it wasn't constant, it would change the question dramatically. Sketch a graph of the height of water over time. Okay, so think about the height of water. And so in general, as I'm pouring water, like visualize it happening. Water is pouring into the container. What will happen to the height over time? It'll increase. Very good. Right? Is it going to decrease? Ever? I don't think so. How can you pour water into something and it decreases? Say, well, what if it splashes a little bit out or something? But no, like it's going to increase until it gets to the top and then overflow, and it won't decrease, but it'll stop increasing, I suppose. Right? But it won't, like you don't pour water in and the height of the water somehow decreases, right? So it's always going to increase. I think that makes sense. It's how fast is it going to increase, and what will that depend on? Like visualize that for a minute. What do you think? So if the width, so this one begins with a smaller width and ends with a bigger width. So think about it. How will that impact how fast the height is changing? Hunter, what do you think?
The height will increase quicker at first and then slow down.
Very good. Okay, so, and I think that kind of, does that make sense to everybody? And then the other thing you do want to think about with these are pictures off the internet. It's a little bit harder to tell, but sometimes we actually use like a line drawing and then it's more obvious. But with these pictures, a little bit hard to tell. But if it's a curve, or if it's changing, like how is that going to impact exactly what the line looks like? So we do want to think about these things as we're drawing them. So basically all we're going to do is sketch a graph, and I think you certainly want to use like a pencil for this, because sometimes you kind of mess up and you have to erase part of it or all of it or something like that. If you do it in pen, it's going to be a little bit tricky. So sketch a graph of the height of the water over time. So it starts quite thin, gets even thinner, but then gets wider. So it's going to start fairly fast, but then it's going to get, well, that's maybe too fast. See what I mean? So it starts pretty fast, but it's going to get even faster, and then it's going to kind of level off. And that sorry, I'm losing my voice. That leveling off, I hope you could tell that my line is curved, because as the glass continues to slope out, it will slow down more and more and more and more and more, right? So it's like a curved line. A lot of people at that point would just draw like a straight line, but it's curving. Does that make sense? So an example or something to think about is if I drew a straight line, what does that mean? And this is where the thinking becomes more profound than grade 9, I guess. In grade 9, they get it, but what does a straight line on this graph mean?
It's a straight cup.
Okay, yep, good. It's a straight cup. What else? How else could you rephrase that in terms of like the height of water over time or something? Yep, Alex? The rate of change is constant. So the height of the water is changing by the same amount every second between every 2 points on that line. And that's not what's happening if the cup is going out like this. So a straight line in one of these graphs communicates something specific. Yes, the height of the water is going up, but it's also going up at a constant rate. And that wouldn't happen if the rate of water going in is constant, but the shape of the glass is changing. The height of the water would change at different heights. Okay? Okay, you try the next one. You might want to think about, this takes us back a little sort of to like even end behavior and interval of increase and decrease. Like there's not a lot of interesting stuff going on. The end behavior and the interval of increase is all kind of the same. But again, those are characteristics of functions that we can use to describe what's happening here. When you say, oh, the height of the water it's always going to increase. You're making a statement about the function that represents the height of the water and the intervals of increase and decrease. That's what you're doing. But we have a formal way in mathematics class of talking about that. Formal notation, formal way of talking about it. But it's the same thing. The thing that you would naturally, I think about, right? That the height of the water will keep going up until it overflows. And so then that's like end behavior, interval of increase, decrease, that kind of thing. Okay, so this one, another thing you might think about is where are the changes taking place? So there's a start, and then something changes there, something sort of changes there, and then something sort of changes there again. Like there seems to be, I would say, those at least 4 defining points where things change. Okay, so let's see if I can do this. So it looks to me like it starts fairly fast. By the way, your sketches don't have to be phenomenal, but if it should be curving, then you should be showing some kind of a curve. Like it doesn't have to be an accurate curve, but it's got to be some kind of a curve. It should never curve down because that would be a decrease in height. We just finished talking about how that's not possible. If it's a straight line, it should look like more or less a straight line. And if there's a change, even it could be hard, I know, but your graph should show some kind of a change. Okay, I should be able to look at it and see there's some kind of a change. So there's no scale. It doesn't have to be accurate that way. Let's see. It starts out fairly steep, but then it sort of slows down. But then it gets steeper, and then it's like quite steep. There's almost a straight line there, so we could kind of go like a straight line for a bit, and then again it slows down. So again, I kind of have 4 parts of the graph after the 4 changes. If your graph looks something like that, it's got like a decreasing happening here and then another increase, and it's a little bit straight for a bit and then another decrease. That's good. Okay, you're on the right track. Try the last one if you haven't already. It's easier. So I started out fast, slowed down a little bit in the middle of the cup, ended up fast again as it gets to the top of the cup. No arguing, oh, my diagram was only for half the cup. No, you're supposed to draw like the whole container, right? Okay. Any questions about that? Just it's an activity, question like that could appear on a test for sure, and it just gets you thinking a little bit about rates of change and that sort of thing in real life situation. Okay, let's take a look at a application here. Kiva drains water from a hot tub. That's going to take a long time. The tub holds 1,600 liters of water, and the volume of water in the tub is given by this equation where V is the volume in liters after T minutes. Determine the instantaneous rate of change after 30 minutes. So why would this be an interesting question? Well, first of all, let's just think about, like, we're trying to think about functions, everything we know about them all the time. So this is a quadratic function. What's the vertical intercept? It's 1440. So at time 0, that's what it starts at. This says it's a 1600 liter tub, but I guess it's got a little lip at the top. So it's not all the way full, but it's close. That kind of makes sense, right? Like, I can kind of make sense of that. And it opens upwards. I think that also makes sense, that it starts up and it's decreasing, right? So that kind of makes sense. And then near the bottom, we'll talk about that a little bit more at the end. The last thing I want to think about here, what was it? Oh, why would it have a quadratic? Why wouldn't it be like a constant flow of water out of the tub?
Because the tub isn't
Okay, so it may not be a nice rectangle. There's another reason. If you take calculus again, you'll see questions like this very often. Silos of grain that are draining or something like that. Yeah, and why is that? Because the water being pushed out of the hole has less weight on top of it, right? So it will flow. It won't flow as fast because there's not as much water pushing it down. But when there's more water above it, it will flow faster. And you've probably experienced that sort of thing at some point in your life, draining a cooler or something like that out of the little plug that you have. Flows really fast at first, and the last little bit kind of drips out. Okay, so that kind of makes sense again if you think about it. So what are we going to do? Determine the instantaneous rate of change. So we are going to find the slope of the tangent at that point. Okay, so that's all this turns out to be. So at t equals 30, I'm going to find v at 30, and then I'm just going to go ahead and solve. So you can get started working away at that. Did you get 810? Okay. Make sure we're sort of starting with the right numbers at least. So you should have something that looks something like that. don't know if you could tell, but if you look up here for a second, so I was working away at this, and I got to this point, and I'm like, okay, so 0.1 times 900 is 90, and I'm like, wait a minute. There's no, how am I gonna, it's gotta, remember the constants have to add to zero, and I'm thinking, how are these gonna add to zero? 1440 and 720. I mean, those are in the ballpark, but that's still, they're not gonna add to zero. And then I'm like, I forgot to subtract. So I forgot this when I was first doing it. I forgot to subtract 810, right? So immediately I thought, oh, I'm missing something important here because it's not adding up. I forgot 810, so see how I added it? See how all my lines magically got longer? And of course now it's going to, what I call the moment of truth. Are the constants going to actually add to zero? And they do, so I'm good. But that's a big common mistake, right? It's just easy to make because you get right into the algebra and you forget to subtract that. You forget to subtract, in this case, v at t. So for me, they do cancel out. Is everybody pretty much got that? So I got negative 18. Does that answer make sense? Do you like that answer? What makes sense about that answer? Right. Right? It's decreasing. So that makes sense. Of course, the volume, it's V at T, right? Go back up. It's always useful to go back up and think about what the variables represent. V is the volume in liters. So the volume is decreasing. Like if I have to write a final statement here, this is therefore the volume is decreasing by 18, well, hold on, what? So then liters, I guess, liters per minute, right? Volume liters per minute. Very nice. Any questions about that? So that's what rate of change means. That's what the like finding the slope of the tangent, the instantaneous rate of change. Here's the graph. So you can see that it's steeper up here. And then if I could try to draw in a slope of the tangent like that, but then it's going to get less steep here. So as you get less water and you get down near the very end, there is going to be, it's going to be very slow, right? The rate of change is going to get very slow and eventually hit zero. This part of the function in real life won't exist. It's not going to all of a sudden magically start filling up unless you put a hose into it, right? So once it hits zero, that's it. The water's gone. But it makes sense. It's, again, we can see now why a quadratic works. It starts off faster, and then in the middle, it's still going pretty fast after 30 minutes, and then it slows down at the end. The volume of water, the rate of change, the volume of the water flowing out of the tank, right? Okay, good. As you're working on this, think about what the rate of change represents. Visualize it, think about it. Think about what the vertical axis represents, what the horizontal axis represents, that sort of thing. Okay, just one more example to do today. And we're going to take a bit of a different technique on this one, just a slight different one. Remember when we did slope of the tangent, we did sort of, there were two examples. And one of the examples, we found an expression for the rate of change or expression for the slope of the tangent at any point. Why will that be useful in this one? Because it wants us to do it, it wants us to figure it out when t equals 3 and when t equals 1. So if I ever had multiple of these to do, I would find an expression for the slope of the tangent first. We call this the fully simplified difference expression for the difference quotient. Okay, the textbook calls it that. It's kind of a mouthful, but okay. And so we would find that fully simplified expression for the slope of the tangent, and then, or the instantaneous rate of change, and then we can easily find it for any value, any time value. So in this case, Ted's throwing a rock off a bridge. The height of the rock over time, there's the equation given for the height of the rock over time. H is in meters, time is in second. What's the instantaneous rate of change? Okay, so how does this one look a little bit different? Slope of the tangent equals, we're still doing the limit as h approaches 0 of h. This is a bit confusing because it's h and then t plus h is a different h. Some people like to change the variable. I'm going to leave it the same, but some people do like to change the variable here. So t plus h, it's going to be gone in the next part anyway, minus h at t over h, which equals, I'll get you started and then I'll let you try to do some of the algebra. So when we sub in, we're subbing in t plus h for well, these should be t's, for the t's in here, right? So it's negative 5t plus h squared plus 15t plus h plus 23.75 minus, and usually we would have a number here, but when we're finding an expression, we're actually subtracting negative 5t squared plus 15t plus 23.75. Okay, so give that a try, start expanding and simplifying and see what you can get. You want to check after you've done sort of one line? Okay, so I'm still expanding this part, but a bunch of these things cancel. So I saw that there was a plus 15t and a minus 15t, so I just canceled them. And a plus 23.75 and a minus 23.75, so I got rid of those. Kind of got rid of things as I went in this case, because you get a lot of things that are the same but opposite signs. Okay, so I'm left just with a couple of things. And then same thing happens after I expand this. Those go away. So all of the terms without an h in them they end up canceling. That should happen. And in this case, I'm left with 3 that have an h. So I rewrote those, factored out the h, and then I can divide those to 1. So negative 10t minus 5h plus 15. And when I set h equal to 0, the slope of the tangent is 15 minus 10t, or negative 10t plus 15. Such a nice, like, simple expression in the end. Remember what I've been saying over the last few days. Is it the concepts or is it the algebra that you're getting stuck up on? So if some people are still busy scribbling, trying to get it all down, or you made a mistake and it's not working out, it's the algebra, right? You just got to keep practicing and get to a point where you're not making those algebraic mistakes. Now, what is this actually asking us about? What is the instantaneous rate of change when t equals 1? So now that I have this expression, I can answer these questions. At t equals 1, the slope of the tangent is negative 10 times 1 plus 15, which is 5. And at t equals 3, the slope of the tangent is negative 10 times 3, plus 15, which is negative 15. This was the height of a rock thrown off a cliff. Somebody tell me a story that's happening here. Interpret this. What information can we figure out about this function or about this situation from the information that we've gathered here? Alex, what do you think? Do you have a no? Okay, Hunter, what do you think?
And at 1 second, it's still in the air, it's going upwards.
Very nice.
But then at 3 seconds, it's starting to go downwards.
Okay, good, great, right? So the particulars, the fact that it's at 5 meters per second and 15 meters, whatever, right? But yeah, exactly. So in other words, the vertex of the quadratic has occurred somewhere between those 2 points. It was increasing, now it's decreasing. It's gone through a turning point. And magically, I've got this one drawn for us right here. So there you go. There's the first one. It's positive and it's not as steep. And there's the next one. It's negative. So there's the path of the rock and it has hit its maximum point and now it's coming down and you can visualize what's happening here. Does that make sense? And you sort of see the value of this, how we're really starting to get some information about this picture. Why would a physicist be interested in knowing the exact rate of change, the exact speed of a rocket or a satellite that's coming out of its orbit and falling back onto the planet? Like, why would it want to know those exact things at exact times, at exactly 5 seconds? What's its rate of change? But clearly, somebody would want to know those things, right? So here we go. Now we can go ahead and calculate all those things pretty quickly. Okay, so a couple of sort of thinking questions in page 104. Like there's a couple of those liquid container questions there. And then, the handout is only posted. It's got a bunch of questions on it, but you can start with those ones, 1, 2, and 4. So it's posted to the classroom. I don't have paper copies. And then 3 questions in the textbook. Okay? Any questions?